Hello everyone, so I'm Michał, and together with Paweł and Alicja, and also a team from NVIDIA, Daniel and Adrian, we worked on diffusion-based text-to-speech models, and yeah. So first of all, a short background, introduction to diffusion. Probably some of you have heard, most of you. Diffusion is the current state-of-the-art in image generation. The base idea is this top part where we can see a noising process of an image. So on the left there's a normal picture and we can add some noise to this picture. And adding noise is quite easy. What's more interesting is going from right to left to subtract the noise without knowing it. So what we can do is we can first train a network that will predict what kind of noise there is on the image. And this is a basic image-to-image network, so it can be a unit or a transformer-based model. And when we have that, we can use this network to make this the noising process, where at the beginning we just randomly sample some noise, and then we subtract the predicted noise from the image in small steps. Yeah, that's the base of diffusion. And now, how can we connect diffusion with text-to-speech? Because diffusion generates images, and text-to-speech is between text and speech, so the image part is not that obvious. But fortunately, the speech can be stored as a waveform, but also we can store it in mail spectrograms, which looks like this, and it's like a more compressed version of this waveform. Yeah, so we will just focus on using the diffusion to generate mail spectrograms. And here on the right-hand side, you can see architecture of Tortoise, a model recently presented that's achieving a very good quality results in generating speech. What's interesting is that as the input, it takes just the text, but also some conditioning samples, which could be like 5 samples of, I don't know, 10 seconds or something like that. And it can generate a speech that sounds like a specific human or specific in a specific way. And in this network there are 2 most important parts. So first one is this autoregressive transformer, which is just an NLP that creates an input that is taken to the diffusion decoder, which is the part that generates mail spectrograms using diffusion. And when we have a mail spectrogram, generating the output waveform is just done using a vocoder, which is like the simplest part of this whole algorithm. Yeah, so this model is called Tortoise because it's TTS, like text-to-speech, but also it's quite slow. So in our project we wanted to focus how can we speed this up. Next slide, please. Okay, so there was this paper in December called On Distillation of Guided Diffusion Models. It shows us how can we speed up diffusion by changing the model. So the first part is about guided diffusion. It's a technique commonly used in most of the diffusion networks that we use not only the conditional model, but we also use the unconditional model, and in the denoising process we create this linear combination of those 2 models, and we just use the forward passes of 2 models and we combine them, and it happens to behave better. It's more regularized and the outputs are better quality. So the idea is to distill those 2 models into one, and we just train this one model that will behave like this linear combination of 2 models. So that's the first idea. And the second idea is to use progressive distillation, which is a way of training a new model that will make bigger diffusion steps, twice as big as the original model, and we can repeat this process. So if we repeat it 2 times, we have a model that creates 4 times as big steps, so we can use 4 times fewer steps in inference to make it faster. It has a slight, it changes the quality a bit, but it's still an effective way of speeding up the diffusion models in general. Yeah. So we decided to use this approach in the Tortoise network, and Paweł will now show us the results.
Okay, so I'll take over to talk about the 3 models that we created during our experiments that we'll be comparing. Okay, so we started by taking the diffusion module from Tortoise, and we fine-tuned it on our dataset, and this will be our baseline. So it was trained to use 4,000 diffusion steps during training, but during inference it was actually inference with only 80 bigger inference steps, as the authors find out that this is sufficient to generate good quality voices. On the bottom row you can see the generated MER spectrograms with these models, so we can see that the MER spectrogram generated with the teacher model looks quite good, and we can also hear how it sounds.
What sort of business can a young man go into without capital?
So it sounds quite good. And we took this model and we performed the distillation process that was described on the last slide. So we performed guided and progressive distillation. We did 7 steps of progressive distillation, so the steps that the model was trained on reduced from 4,000 steps to 31 steps, and we also used the same setting during the inference. And as we can see, the MER spectrograms also look quite good, and they are pretty similar to the teacher one, and we can hear how they sound.
What sort of business can a young man go into without capital?
Okay, so both this model differ in training setup and inference setup. So we also chose a model that is something in between them. So we took the teacher with the same weights as the leftmost model, and instead of inferencing it with 80 steps, we inferenced it with this faster setting, with the same setting as the distilled model. And as you can see on the MER spectrogram, it looks quite noisy, quite messy, so we should expect much lower quality of the sound, so we can hear it. Okay, so now let's see what are the more quantitative results. So we perform a test where we take 4 people and we gave them pairwise comparison. So each person received 100 pairs of sounds to compare, and they voted which one is better or reported a tie if they were unsure. So we first compare the teacher model with normal setting with the distilled version, which is our version. This is the plot on the left, and as you can see, they are undistinguishable. They receive the same amount of scores from our people. Okay, and on the right we can also see the results of this distilled model versus the teacher, which the inference process was blindly replaced with this faster one. And as we can see, it's pretty simple to distinguish between them, and our model was reported 100 times better than this version. Okay, so our model's quality is as good as the teacher one. What about the latency? So we measured the latency and reported over 4 or 5 times speed up of the inference process. And this is unsurprising, as our distilled version uses over 2.5 less inference steps during the inference. And also each of the inference steps is using only 1 forward pass of the model instead of 2 forward passes that the teacher one uses. Okay, so that's all. Thank you for your attention. Are there any questions?